Hello everyone. Today I am going to discuss about the estimation of the regression parameters beta and the error variance sigma square of the multiple linear regression model. This lecture is based on the syllabus of BSc CBCS 4th semester statistics honors paper linear model, which is taught in the colleges under Dibrugarh University. The multiple linear regression model can be expressed in scalar form as y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 beta k xk plus epsilon. Here epsilon is the error term. And so here we will discuss about the ordinary least square estimation of beta parameters of the multiple linear regression model. Here, no distributional assumption on y are required to obtain the ordinary least square estimate. For the parameters beta naught, beta 1 up to beta k, we seek estimators that minimize the sum of the squares of the deviations of the n observed y's from their predicted values y cap. So we seek beta naught cap, beta 1 cap up to beta k cap that minimize the least square functions. This one. This is the least square function summation over I from 1 to n epsilon I cap square, and this is nothing but this epsilon I cap square is nothing but yi minus yi cap whole square, and this is the in extension we can write yi minus beta naught cap minus beta 1 cap xi1 minus beta 2 cap xi2 dot 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 beta k cap xik whole square. Here it is to be noted that the predicted value yi cap equal to beta naught cap plus beta 1 cap xi1 plus beta 2 cap xi2 plus dot 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 beta k cap xik estimates expectation y, I not yi. So to obtain the ordinary least square estimators, it is not necessary that the prediction equation yi cap be based on expectation yi. It is only necessary to postulate an empirical model that is linear in beta cap, and the ordinary least square method will find the best fit to this model. Now to find the values of beta naught cap, beta 1 cap up to beta k cap that minimize the least square function, we could differentiate summation I from 1 to n epsilon I cap square, that is the least square function with respect to each beta j cap separately, and set the result equal to 0 to get k plus 1 normal equations. One for each of the unknown regression coefficients there, beta naught, beta 1 up to beta k. So the solutions to the normal equations will be the ordinary least square estimators of beta naught cap, beta 1 cap up to beta k cap. The least square function can be rewritten as S equal to, this is the least square function, and we can summarize as summation over I from 1 to n yi minus beta naught cap minus summation over j from 1 to k beta I cap xij whole square. So this is the least square function. This is equal to S. The function S must be minimized with respect to beta naught, beta 1, beta k, and the least square estimators beta naught cap, beta 1 cap, beta k cap must satisfy these equations. This is the partial derivative. This is the partial derivative of the least square function with respect to beta naught, and we make it equating to 0. And the second one is the, here we have k normal equations of del S, del bi. I takes the values 1 to 3 up to k, and the normal equation is this one minus 2 summation I from 1 to n in bracket yi minus beta naught cap minus summation j from 1 to k beta I cap xij bracket close xij equal to 0. So simplifying these two normal equations, we obtain the least square normal equations after simplification. Here there are k plus 1 normal equations, and we have k plus 1 unknown parameters, and we get the estimated parameters beta naught cap, beta 1 cap up to beta k cap by solving these k plus 1 normal equations. And these beta naught cap, beta 1 cap up to beta k cap are called the least square estimators of beta naught, beta 1 up to beta k. Now the ordinary least squares estimators for beta in matrix form. It is more convenient to deal with multiple regression model if they are expressed in matrix notation. This allows a very compact display of the model, data and the result. In matrix notation, the model can be expressed as y equal to x beta plus epsilon. And if you write all the matrices, we get this type of expression. Here it is the y vector, this is the x matrix, this is the parameter vector beta naught, beta 1 up to beta k, and the last one is the error vector epsilon 1, epsilon 2 up to epsilon n. So in general, y is a n by 1 matrix vector of the observation, x is an n by p matrix of the level of the regression variables, beta is a p by 1 vector of the regression coefficient, and epsilon is an n by 1 vector of the random errors. Here p is nothing but k plus. So now we want to find the vector of the least square estimators beta cap that minimizes this least square function, summation I from 1 to n epsilon I cap square. And in matrix notation we can write this one is nothing but epsilon prime epsilon, and this is nothing but y minus x beta prime, y minus x beta. And after simplification of this expression, we have y prime y minus twice beta prime x prime y plus beta prime x prime x beta. So in this expression, beta prime x prime y is a 1 by 1 matrix. That is, it is a scalar quantity, and therefore its transpose beta prime x prime y whole thing prime, nothing but this is y prime x beta. This is also the same scalar value. So the least squares estimate must satisfy del epsilon prime epsilon by del beta. We have minus 2x prime y plus 2x prime x beta cap equal to 0. And after simplification, we have x prime x beta cap equal to x prime 1. So this is the ordinary least squares normal equations. And to solve these normal equations, we multiply both sides by the inverse of x prime x. We multiply this term by x prime x inverse, and with this term also x prime x inverse. And after simplification, we have beta cap is equal to x prime x inverse x prime y. But the condition is that the inverse of the matrix x prime x inverse must exist. So the x prime x inverse matrix will always exist if the regressors are linearly independent. That is, if no column of X matrix is a linear combination of the other columns. So after finding the estimated regression coefficient beta cap, the fitted regression model corresponding to regressor variables x prime, this is that is 1 x1 x2 up to xk becomes y cap. This is equal to x prime beta cap. This is nothing but beta naught cap plus summation I from 1 to k beta I cap xi. So the vector of fitted values of yi cap, these are the estimated yi cap corresponding to the observed value yi is y cap is equal to x beta cap. To put the values of beta cap here, we have x prime x inverse x prime y. This is hy, where h is x prime x inverse x prime. This is called the hat matrix. This is a n by n matrix. The difference between the observed value yi and the corresponding fitted value yi cap is the residual epsilon. That is yi minus y cap I. So the n residuals may be conveniently written in matrix notation as epsilon cap equal to y minus y cap. And this can be written like this with the help of the hat matrix 1 minus y h. So the estimated residual factor epsilon cap can be used to check the validity of the model and associated assumptions. Now we are going to estimate the error factor sigma square. The method of least squares does not yield a function of the y and x values in the sample that one can minimize to obtain an estimator of sigma square. However, we can derive an unbiased estimator of sigma square based on the least square estimator beta cap. With the help of the estimated value of beta parameters, we can estimate sigma square. By assumption 2, sigma square is the same for each yi. This is a constant variance for all y, and thus sigma square can be defined as sigma square equal to expectation yi minus expectation yi whole square. This is the basic definition of sigma square. So, and by assumption y, we obtain expectation y is nothing but beta naught plus beta 1 xi1 plus beta 2 xi2 dot plus beta k xik. This is nothing but xi prime beta, where xi prime is the ith row of the matrix X. So thus sigma square becomes expectation yi minus xi prime beta whole square. So this is the expectation of this term. So we can express this expectation in average as S square is equal to, this is the estimated value of sigma square, 1 by n minus k minus 1 summation over I from 1 to n yi minus xi prime beta k. So here n is the sample size and k is the number of x's. So we can write this in matrix form, this term in matrix form as 1 by n minus k minus 1, 1 y minus x beta cap prime into y minus x beta prime. This term in matrix form. So after simplification of this term, we have y prime y minus beta cap prime x prime y divided by n minus k minus 1. And this numerator, the term in the numerator is nothing but sums of squares due to error divided by n minus k minus 1. So here that with the denominator n minus k minus 1, the s square, that is nothing but SSE divided by n minus k minus 1 is an unbiased estimator of sigma square. So dear student, I conclude today's lecture here. Thank you.